Hello, everyone, and welcome. My name is Rula Deeb. I'm a senior principal at Geosyntac Consultants and the coordinator of the webinar series on behalf of SERDP and ESTCP. I will be facilitating today's event. This webinar focuses on DOW-funded research efforts to develop my apologies. I'm having some technical difficulties here. To develop practical tools and assessment approaches to improve the design, operation, and resilience of cold regions infrastructure. The webinar will feature two speakers, Dr. Tom Douglas, who will present best practices and standard operating procedures for the design and safe operation of linear infrastructure on seasonally frozen terrains in Alaska and other high latitude locations. Our second speaker will be Ms. Margaret Kurth, who will discuss a coupled installation community approach to assessing infrastructure resilience in cold regions, including updates to existing mission resilience tool and a new method for calculating resilience return on investment. Each of the two speakers will have the opportunity to participate in a Q&A session at the end of their presentations. On the next few slides, you will have instructions on optimizing your webinar experience. If you have difficulties downloading Zoom, you can view your slides using an internet browser, such as Firefox, IE, or Edge. Alternatively, you can refer to your webinar registration confirmation email and download Zoom or call into the conference line provided to you. If you continue to have difficulty viewing the slides, or if the material is not showing on your screen, or if your screen freezes, please feel free to hit Control and F5 to do a hard refresh of your browser. As a reminder, you can download a PDF of the slides at the webinar webpage. We're going to drop that link in the chat box right now. And you can follow the slides in the PDF and call into the conference line to hear the speakers. Another alternative way of following today's proceeding is to go to the SERDP and ESTCP YouTube channel at the link shown here, as we plan to be broadcasting live. And if you have any questions for our speakers, we ask that you please use the Q&A box on your screen at the bottom and input your question. We ask that you add your organization name at the end so that we can identify you during the Q&A sessions. The chat box should be reserved for technical difficulties that you're experiencing, and the webinar team can respond to you in the chat box. Please use the Q&A box to submit your questions. And at this point, it is my pleasure to introduce Mr. Kevin Hyers, who serves as the SERDP and ESTCP Program Manager for the Resource Conservation and Resilience and the Natural Hazards Adaptation Program areas. In these capacities, Kevin is responsible for identifying strategic research needs to support conservation, ecosystem management, and wildland fire management on DOW installations. Kevin brings nearly 30 years of experience at the interface of natural resource management and science. His academic and management work have both focused on fire ecology, conservation of threatened and endangered species, and the science support of prescribed fire modeling to meet ecosystem management objectives. Kevin received his master's degree in conservation ecology from the University of Georgia. Kevin, please proceed.
Thank you, Rula. Welcome everyone to today's SERDP and ESTCP webinar. The next few slides will provide a quick overview of these programs. SERDP and ESTCP are the Department of War's installation innovation programs aimed at developing and demonstrating innovative, scalable technologies that enhance military readiness, improve warfighter capabilities, and strengthen the department's infrastructure. These programs prioritize common sense, cost-effective solutions that support operational effectiveness and reduce regulatory burdens at military installations. SERDP invests in basic to applied research that supports and secures military installations. It is managed alongside its partner program, ESTCP, which demonstrates and validates novel technologies for military installations. ESTCP demonstrations collect unbiased cost and performance data to supply installation managers and end users with the information they need to implement approved technologies and facilitate DoW adoption at scale. SERDP and ESTCP report to the Deputy Assistant Secretary of War for Energy, Resilience, and Optimization, headquartered at the Pentagon. We work closely with our other OSW programs, the services, and installation partners to facilitate the adoption of successful technologies. By fostering cross-program integration, we ensure that promising innovations do not remain isolated efforts, but transition effectively to operational use. Our programs align with national security priorities and provide the data and capabilities that DoW leadership need to shape guidance aimed at securing our military installations. Our science and technology protect built and natural infrastructure, strengthen supply chain resilience, and ensure the health and safety of our warfighters, their families, and communities. Our research portfolio is organized around 6 program areas. The Environmental Restoration Program area focuses on managing PFAS and other emerging chemicals of concern in the environment. Resource Conservation and Resilience Program areas focuses on sustaining the 28 million acres of DoW lands for test and training operations. The Weapons Systems and Platforms Program area focuses on strengthening DoW's long-term chemical and material resilience, extending the service life of mission-critical weapons systems and platforms, while reducing costs and enhancing the safety and efficiency of military operations. The Installation Energy and Water Program area demonstrates and validates technologies that improve access to reliable and resilient sources of energy, ultimately providing greater flexibility to the control and delivery of power. The Natural Hazards Adaptation Program area demonstrates innovative and cost-effective technologies to ensure DoW installations can withstand and recover from events such as earthquakes, hurricanes, floods, and wildfires. Finally, the Munitions Response Program area focuses on unexploded ordnance in the underwater environments, including ponds, lakes, rivers, estuaries, and coastal ocean areas. After years of successful investment, this program area is currently transitioning technologies to end users through a series of test sites and live site demonstrations. SERDP and ESTCP are a critical funding source and partner for hundreds of federal, university, and industry R&D efforts. We release solicitations throughout the year. Researchers from federal government, private industry, and research institutions can apply to both SERDP and ESTCP funding opportunities. To receive updates about funding opportunities, our programs, and upcoming webinars, you can sign up for our mailing list at the link on this slide. Our webinar series highlights outstanding projects across all our research portfolios. You will find additional information about upcoming webinars at this link. All past webinars are archived and can be accessed using this link. At this point, I'll turn it back over to Rula to introduce today's first speaker. Thank you for joining us, and I hope you enjoyed today's webinar.
Great, thank you so much, Kevin. It is now my pleasure to introduce today's speakers. As mentioned, we have 2 speakers who will speak on today's topic, and the first one will be Dr. Tom Douglas, who is a Senior Scientific Technical Manager for the U.S. Army Corps of Engineers Cold Regions Research and Engineering Lab at Fort Wainwright in Alaska. Tom's research is focused on characterizing permafrost, snow, and ice through all-season field surveys, geophysical measurements, and remote sensing. His projects support training in land management and maneuvering, help design and operate a variety of infrastructure, and provide insights into changing Arctic terrains. He currently serves as co-lead of the Interagency Arctic Research Policy Committee Risks and Hazards Team, and is the United States lead for the Environmental Working Group of the International Cooperative Engagement Program for Polar Research. Tom received a master's degree in geology from the University of Alaska Fairbanks and a doctoral degree in earth sciences from Dartmouth College. Tom, please get started.
Okay, thank you, Rula, for that introduction. And yeah, I'm really excited to speak with you all today. I appreciate everyone's time. Happy Thursday morning from Fort Wainwright, where I just noticed it's now minus 25 outside. So probably, we'll go do a snow dance or something. So an overview of this presentation focused on linear infrastructure. I show these photos on the upper right quite often just because I think it's very illustrative of kind of what we're dealing with up here. So right now, looking outside, we're at sort of that upper left photo. It's frozen, there's snow. You could kind of drive almost anywhere if you could get through our 5 or 6 feet of snowpack. But it's hard to think, but in about 6 to 8 weeks will be the upper right photo, which is kind of right after snowmelt. And still the ground's quite frozen. The active layer is totally frozen. You could kind of go anywhere. The lower left is peak, vegetation kind of June, July, August timeframe. And we start to get that kind of top-down seasonal thaw. And then the lower right is kind of heading right back towards the snow, the winter world. So today I'm going to give an overview of the training land domain here, talk about some key infrastructure types they're somewhat unique, but also relate to other places. Talk about our project activities and then ongoing efforts and benefits. And I want to say I've got a ton of co-authors on this project, sort of a dream team in my mind. Their names and their various roles will come up as we go along. I also want to thank ESTCP, U.S. Army Alaska, the Public Works folks, environmental, range control, the planning folks, 11th Airborne, and Michelle Michaels with the Alaska Innovation Landscape Network. So here's a map kind of showing our area. The key thing, it's about 1.5 million acres. I think you can kind of see this is an elevation map, so sort of the low-lying areas. The red boxes identify the major training lands. They're unfortunately not labeled here, but I'll scroll over the mouse just a touch. So this one below Fairbanks is the Yukon, or is the Tanana Flats training land. There's very little access to that, but it's used quite a bit. You can get there by boat or air or in the winter over the ice. To the east of there is the Yukon training range, training area, which is, you can see, kind of mountainous. There's lots of roads, all season access to roads there. Moving south of Delta Junction is the Donnelly training area, which is also broad and fairly sprawling and largely inaccessible. So varied ecology, geology, there's uplands and lowlands. Think about that seasonality and the different land use. You can take advantage of some of that seasonality with land use, but then other times it's challenging. And as the 11th Airborne trains over more and more of these lands over all seasons, there'll be kind of expanded need and use for infrastructure. Maybe hard to see all these squiggles, but kind of focus on the different colors. And again, these training lands, you can see various seasonal trails in that kind of orangey color. The blues are fens. It says airboat trails here, but when I talk about fens later, that'll make sense. You see fire breaks, and I've got the kilometers that they have to deal with. And again, remember, there are not a lot of roads here. So a lot of the access to manage or develop or expand or modify these types of linear infrastructure is quite challenging, seasonally dependent, and of course gets expensive fast. A quick intro on permafrost. Hopefully there are some fellow permafrost lovers out there, but just quickly, here's a map of most of the kind of Arctic permafrost region. You see Alaska in the lower right. The key thing to mention here is in our area, in sort of the boreal permafrost of interior Alaska, it's what's called discontinuous. And I liken it to blobs in a lava lamp. Sometimes it may be the top of near surface permafrost might be meters below you, or it might be right towards the surface with kind of a classic active layer. So finding it can be a challenge. And obviously, if you can find it, you may want to work to avoid it. It tends to be in valley bottoms, north-facing slopes, poorly drained soils, or places where vegetation, that classic ecosystem protection that I'll probably mention later, allows it to thrive in our kind of -1°C mean annual temperature. So on to kind of the first, basically we had 6 main efforts for this, and these are all these different infrastructure types. And for each one, we kind of followed a similar pattern of best practices, talk to folks on Fort Wainwright and other places, Canada, other Arctic locations, look through peer-reviewed literature, look through Army doctrine, learn about the infrastructure type, and then we developed a technical report, and you'll see links to each TR as we go along. Lauren Boucher led this section, and you can imagine in Alaska, summer roads, fire breaks, drop zones, these are a pretty big deal, especially for summer training. And obviously fighting wildland fire, but you can see in the lower right, that tank is quite stuck there, and so obviously that's an impact of the training land. It also could lead to wasted effort trying to get that thing out, and so trying to make sure you avoid that is sort of a key thing, and also protecting that permafrost. So that bulldozer in the upper right is clearing that surface vegetation, which again is kind of very key and critical to keep permafrost happy. So what did we do? We looked also from our work and others at some types of technologies that maybe you can use to track how your permafrost is doing, maybe after you develop these things. Repeat LiDAR works really well. You can see, centimeter scale changes if it's ground subsidence or water table elevation. And then radar and resistivity work really well too. And most of these reports are hundreds of pages long. So distilling it into one slide or two, realize it's quite a bit of a summary going on here, but sort of clearing in the winter, protect that organic mat, literally putting wood chips down, and monitoring correctly are some good ways to sort of mitigate that thaw. All right, so I guess hopefully this works. Get your phones ready. I tested it. If for all of these, I'm going to have kind of a summary slide with the left, which will be sort of the photo of this technical report. They're all available online. If you want to email me, I can send you a link to them. Some are too big to email. That QR code should link you to this fire breaks one. And then while people are, eagerly getting their cameras out to get that QR code, I'll just mention the upper right shows a really nice example of some repeat LiDAR, airborne LiDAR we've done. You can see some degrading polygons. This is at the Creamer's Field site here in Fairbanks. And when you subtract the 2010 ground surface, or the 2020, sorry, from 2010, you can see subsidence, those browns of up to 4 meters over 10 years due to melting ice and thawing permafrost. Okay, so on to the next one. Low water stream crossings. This was a sort of a fascinating one, led by Paige Tobin. You may remember in the news about 10 years ago, 9 soldiers at Fort Hood died because they got swept away in a low water stream crossing flood event. And so the goal here was to update the 1980s Army doctrine for these. And Paige has an incredible report with a lot of engineering diagrams and some case studies. This one on Jarvis Creek is a pretty neat case study. It's actually a glaciated terrain. It's the only one that the DOW manages across their training lands. And I think a key point of this is when you think about flood events, let's say Texas or anywhere else, you're thinking rain, right? Big rain events, monsoon type things. This one tends to flood on a really hot day in August because the snow and the ice are melting in the 2 glaciers upstream. And that's very difficult to monitor or even predict, right? Sort of how hot is it, how much snow is melting. So that's a good example that we use as a case study, but we also reviewed a whole slew of other low water stream crossing, protocols and whatnot. And we've just started a collaboration with the Republic of Korea for winter operations on some of their rivers and even lakes that they have to cross, and how they do that kind of summer versus winter. So here's the QR code for the low water stream crossing technical report. And again, as I said before, you can contact us and find them. Okay, I'm going to move on. Thank you. All right, so wetland features. So you remember I mentioned fens earlier, that kind of turquoise squiggles. There's other types of wetlands up here, of course, but I'll maybe just talk about the fens a little bit. These are tens of kilometers long. They're extremely low gradient. They're oftentimes accessed by airboats in the summer. And actually, the lower photo, you can see that thin line through the green vegetation, and sort of gorgeous picture of fireweed right there. But that's basically an airboat trail. And there's a bit of a hydrology that the airboats can sometimes do to the fens, but we were more focused on that upper right. These are, especially for the 11th Airborne Division, these provide areas, sort of mode of maneuver. You can imagine going on skis, landing helicopters, maybe even jumping into these. And so there may be an infrastructure type, I sort of say that in air quotes, that could be used in the winter, but of course in the summer they're quite challenging. So similar, kind of looked at different methods, looked at land managers and biologists. Fish and Wildlife Service, of course, these fens are all over Alaska, so they have a focus and an interest in them as well. And then Fort Wainwright, again, they're pretty amazing up here. They've got these fens. There are a few other places where the Army has to manage these on training lands, and so working with them, in getting a sense of what their best practices are, we were able to put this report together. So some of the findings, ice, being able to land helicopters or vehicles or people, using them across ice, using various guidance that's been long established for, ice thickness versus, is it someone on skis, someone on foot, a track vehicle, a large vehicle. And then, as mentioned before, kind of LiDAR and geophysics can work pretty well at giving you a sense of, water table over time, the status of permafrost along the sides of, typically sort of constraining these fens. And radar can also help you with ice thickness if you want to know that semi-remotely. And here's the QR code for the fen with a photo there. That's basically a recent wildfire that came along the side of a fen. So you'll see in the upper right the sort of lighter tan color. That's the fen, but you can watch. This was a fire that happened in 2010, and I took this photo in 2011. So you'll see actually a bit of grass, really bright green grass has kind of come up around the fire perimeter. But this is an area where probably that permafrost is going to thaw. It has. We've been studying this for the last 15 years. And so that fen can now sort of leak and ooze and migrate westward as that thaw happens, and we get kind of a subsidence. And so even however you want to manage these for best practices, Mother Nature can get involved too. Okay, so snow roads. This was led by Jenna Williams. And there's been a lot of work on snow roads, and I'll talk about ice bridges in a second. But the Canadians have used these quite a bit. The diamond mines outside of Yellowknife use snow and ice roads. This is a great way to get around in Alaska, and there has been a bit of work on this. And so the idea here was again to sort of synthesize all the various information that's out there. How do you do a snow pit? And oftentimes I'll say a summer road or fire break turns into a perfect snow road, right? Because you can kind of use these linear features in all seasons. I will say our summer season has increased 35 days since the 1970s, and that kind of gotten a little more unpredictable in terms of when it freezes in the fall and when we get our seasonal snowpack. And then, as I said, in a month or so, we'll start melting all that off. So being able to predict that has gotten a little more challenging in terms of shoulder seasons. And the winter actually in some ways has shrunk in terms of its length. So here's the QR code on snow roads, and kind of a classic. Mike Parker and others at Krell study a lot of things to do with maneuver and mobility and whatnot. And so another classic photo of sort of a vehicle navigating the snow challenges. Okay, thank you. On we go. All right. Ice bridge crossings. This is another neat, somewhat unique one. On the right, we're on the Delta River a couple years ago with a ground penetrating radar measuring ice thickness. And the Air Force actually uses a ice bridge or ice road across the Delta River in the winter to get material and equipment and whatnot to their Blair Lakes targeting facility. Otherwise, airlift would be extremely expensive and quite limiting. So, and as I mentioned, Yellowknife, diamond mines, all across Alaska. I mean, there's some Alaska Native, remote villages that use ice bridges and even snow roads for access. The oil companies use them quite a bit. So there is a bit of a literature and some best practices out there. But these can be quite dangerous, right? There's a high risk associated with people or vehicles, wandering across ice. Especially if you have scouring like the Delta River is actually runs year round. So even though you might have a meter of ice in one area, you may have only centimeters in another due to scouring of that river. So radar works really well. And then obviously, site selection is a key piece in terms of where on the reach of the river you would put your ice bridge crossing. And Daniel Van de Voort led this study. And one of this photo from 1968, anyone who's been up on the Hall Road, that's the Yukon River Bridge now. But boy, what a classic use of a very critical ice bridge over the Yukon River. So the last thing I'll talk about is an assessment of airfields. It was led by Jenna Williams. There's 285 of them managed by Alaska DOT. and we were asked to look into a subset of those for NORAD Northcom with a focus on what types of aircraft might be able to access or use a variety of different airfields. And then from there, what type of either future investments or changes to the airfields could be used to allow access to kind of broader airframes. So the upper right lists that set of airframes that Jenna looked at. And so we focused on 23 locations in Alaska and 2 in Greenland. And so these different airframes require, width and length requirements. And so we were basically, and I'm not going to get in, this is a neat report that sort of turns most of these airfields into literally a number and provides a lot of design specs and whatnot. So if you're a pilot or you're working on Air Force needs, I think it's a really nice way to go about that. And so the ability to sort of help this for maybe present or future planning as people need to expand or use different airfields could hopefully be a good guide. The lower right shows a map of the sites that we looked at. We looked at Kangerlussuaq and Patuxent in Greenland, and then 23 sites, or it looks like 24 in Alaska. And again, the QR code. So then a last piece of this project was some terrain sensitivity risk mapping done by Tor Jorgensen. And this is just a map of the Yukon training areas. This is the one that I mentioned has sort of uplands and broad kind of all season road access. Right down sort of where the distance bar is from 0 to 10 kilometers, that area is about where Eielson Air Force Base is. So you can kind of get a sense of we're just sort of east of there, and maybe hard to read, but you can kind of imagine red means high risk. Blue is actually water, but green means moderate risk. And so what Tor did, again, across the 1.5 million acre training land domain is took a bunch of remotely sensed and ground-based information, including work that Krell's done, that he's done, NRCS, Fish and Wildlife, U.S. Army Alaska, just a whole university collaborators, a whole bunch of people, and sort of put these into permafrost maps. And then using temperature and soil information and kind of a model that he develops, he sort of binned the permafrost into sort of 8 what he calls boreal permafrost types. So you can imagine, thaw stable bedrock or gravel moving all the way to high ice content, poor ice cemented silt that's really high risk of thaw. And in this map, you can actually kind of see, like I mentioned earlier, the low-lying areas, the creek bottoms and whatnot have kind of the reds. But this type of work can be used to hopefully help site design and maintain infrastructure as land use and infrastructure planning continues. So kind of starting to wrap up here, ongoing and future activities. We're expanding some of that airfield work to some more sites in Greenland. We're also working on a project above our permafrost tunnel focused on using natural and nature-based solutions. We've got a little bit of an erosion issue on some old trails up there. We're also working on our technical reports, the 6 that I kind of went through. There are various ways to kind of get your information out there. So these are open access PDF, they've got DOIs and whatnot, but there are more formal ways to do it across DOW with things like facility supplements or what they call ATPs or manual supplements. And so we're looking into ways to get these out there. Some may be more amenable than others to do that. And, especially ones with design drawings and whatnot, like the low water stream crossings, may be more amenable. And those are also more broadly used than, let's say, the FENS that might be more of just sort of Alaska specific. We're working on peer-reviewed publications to kind of back up our information with science, particularly some of this thaw risk mapping. In terms of benefits, so U.S. Army Alaska, 11th Airborne, they're expanding their all-season use. It's really exciting, having been working up here for about 25 years. I mean, they're training much more in the winter, even those shoulder seasons. They're expanding their sort of use across the land. So this will lead to probably more use of all these infrastructure types. And wildfire continues to be a pretty major challenge up here. So managing that, accessing it, that'll be a big deal, of course. As I mentioned, these are all open access TRs. The permafrost risk maps are in a paper, Jorgensen et al. 2025. And we, as always, continue to engage with leadership, engineers, and training land managers. So just a couple papers that maybe if you want to zoom in on a couple things for additional resources, this is my last slide. So we have a paper kind of comparing a bunch of different ways to measure or monitor permafrost using geophysics and whatnot, and comparing that to what you might see at the ground surface. So it's this constant challenge of you can easily see the ground surface, and it sometimes provides keys and clues to what's going on in the subsurface, but that can be difficult to link those up. Then this is TOR's mapping, the risk maps paper that sort of spells out with maps and GIS all the training land domains. And then lastly, a really nice paper by Haley Webb, kind of maybe it seems like sort of a nerdy thing, like, oh my gosh, they've defined what abrupt permafrost thaw is. But this idea of thermokarst and sort of ice melt and permafrost and rapid subsidence and whatnot, I think getting people aligned on sort of the terminology and even where these things occur and how they occur will help us sort of move to avoid them or address them in the future. So thank you very much. That was my last slide. Here's info on the presentation number and whatnot for the web, and then my emails here. And of course, you're always welcome to give me a ring and give me a chat. And I think Rula, maybe I turn this back over to you if there's time for questions. Thank you, everybody.
Great. Thank you so much for a great presentation. Just a reminder to everyone, please submit your questions in the Q&A box at the bottom of your screen. We've received a number of questions that we're going to relay to Tom. And here's the first one. How near real time are the geophysical measurements that support risk reduction for the different infrastructure types?
Thank you. So I guess I would say I'll first answer by saying it's getting better. So we have some nice new UAS platforms. For instance, ground penetrating radar on a UAS. We're actually headed to Greenland in a couple of weeks to test that on ice and snow and frozen ground. So I guess I'd say it's getting better. But resistivity is difficult to do airborne and takes a bit of time for a team to do on the ground. So that one may take a little while. Radar is going to get faster and faster, where literally you could fly and probably almost literally real time looking through a computer screen be sort of quote unquote mapping. Most geophysics things, you do need to do some sort of ground truthing. So if it's a summer, you want to thaw probe a little bit, or if you can get cores, that takes a little more time, but you can get a quick look pretty quickly. And then I would say LiDAR is pretty amazing. Within maybe hours to a day or so, you can create a DEM from LiDAR imagery. And similarly, if you do a multiple passes over time, you can make difference maps. But that's not quite near real time. I think the closest one I'd say is radar. That image I showed of the people walking across the ice, literally you are looking at that screen as you're walking and you're mapping the ice thickness. So that's probably the fastest one or the closest to near real time.
Great, thank you. This next question is as follows. At what scales can the permafrost risk mapping be used to design or site infrastructure?
So the scales there that were mapped and kind of modeled these binned 8 boreal forest types of permafrost, I would call that kind of kilometer to sub-kilometer. So that's more sort of, I don't think it would tell you which side of the street to put your building, but it might tell you what end of the street to put your building, if that makes sense. So I would say within kilometers or slightly less. As with any other major construction effort, you'd want to do geotechnical surveys anyway. So I would hope it could sort of lessen the need for doing that broadly and allow you to kind of focus in on maybe a couple top areas and then move from there.
Great, thank you. This next question is from the Coastal Engineering and Adaptation Solutions. What kind of technology, design, innovation, interventions can be used to change least capable airfields to most capable?
Oh boy. I mean, I hate to just say money, but I guess I'll do this really broadly. The least capable airfield would literally be one where there's like a rocky mountain in the way and maybe ocean on the other side. So if you need an airfield of a certain length to get a certain airframe in and out of there, your options are pretty limited and quite expensive. But sort of moving more into kind of reality, access to gravel is a key piece of this. and of course, being able to move material around. And so building or expanding that airfield, whether it's the width or the length of it, is kind of your limiting factor. So I mean, and I don't want to make it sound simple, but yeah, if you have to start blasting or bringing gravel in by barge in the summer only, that's a very challenging airfield to update. Whereas one that has a flat, low-lying, broad plain with gravel nearby would be the easiest.
Great, thank you. Are there plans for new infrastructure on training lands?
Well, so fire breaks, expanding and maintaining them is kind of always a thing in that obviously, when a fire happens, sometimes they got to access it. There are some plans to expand some of the drop zones. They're an airborne division and they do a lot of jumping out of finally functioning aircraft, right, on purpose. And so, especially Husky Drop Zone, which is kind of tucked in there near Allison Air Force Base, there's some plans of expanding that. And there's some out kind of to the west and Donnelly training area that are of interest. So those would be kind of some of the big ones. And then, probably always updating bridges, culverts, monitoring hydrology for low water stream crossings and other ways to cross water bodies is an ongoing thing. Thank you, everybody.
Great. We have a couple of questions related to the technical reports that you talked about.
Okay.
One of them has to do with, based on what was revealed and what you documented in these reports, what is the biggest need for DOW and training lands?
So first one I'd say is some years ago they acquired airborne LiDAR over the entire training land domain. And as I understand, that's planned to be done again probably this summer. That'll be a neat first step because that'll allow a pretty fast assessment of where water is moving or where things are subsiding and where landscapes are changing. I think, as always, you can think about scales, right? So some of this linear infrastructure, there may be hotspots or challenges where literally with your eye, you can see that there's a problem, right? But being able to maybe look at rates of change rather than, oh boy, that pit that we kind of get stuck in every spring keeps getting worse. And so again, being able to remotely assess some of these things over space and time, I think would help them focus their kind of limited resources and time into these various hotspots.
Great, thank you. And the next question that is also related to the reports is from the Pennsylvania Department of Environmental Protection. Do Arctic environmental impact studies differ from terrestrial and or coastal environment impact studies? And if so, what are some of the significant differences? And have you addressed those in your reports?
Thank you. So I guess I'd say, nothing that we did here is coastal. We do have some coastal projects, and so I could talk to you about those maybe separately. In some ways, people that work up here tend to say, oh, Alaska's unique and stuff from the lower 48 doesn't work and all this. But I think in places where you just have seasonal freeze and thaw, and so that could be Pennsylvania, that could be Alaska, there are lots of ways to relate what happens. Obviously, dealing with snowpack and ice are very similar. I think for up here, the seasons are so extreme. We get such a deep freeze, and things are so remote that I would say the biggest issue is just to move equipment or to deal with a safety risk or to reduce hazards. Oftentimes requires planning maybe some seasons in advance and might require aircraft or boats or staging things way in advance. Whereas I think in a place like Pennsylvania, there's quite a bit more road or just access to move things around kind of over all seasons. But I think we can all learn from each other as these various best practices anywhere that we have seasonally frozen and thawed. You don't have to have permafrost to have some of these challenges, especially the hydrology ones too, right? I mean, low water stream crossings, except for the glacier one, a lot of that is a very similar sort of engineering and surveying and hydrology questions. Those are the same worldwide.
Great, thank you. So just to reiterate, because that's the third question that comes in, can the information in your reports be applied to non-Alaskan sites?
Yes. And I guess I would say, please look at our reports. And if you want clarification or you want to see maybe where the limits might be, let us know. We did focus on Alaska sites, so I don't want to make it sound like we will have things that are specific to non-Alaskan sites. So keep that in mind. But again, places where they have seasonal freeze and thaw, I think a lot of similarities will exist.
Great. We're going to ask you one more question and then transition to Margaret. And if there's time at the end, we'll get back to you. So please stay on the line. But before we wrap up, this is a question from the University of Virginia. Does the permafrost risk map assume natural permafrost conditions? And if so, wouldn't the use of permafrost domains impact the thermal structure and change the vulnerability, leading to potential degradation?
I guess, could you repeat that again? That's a lot. I'm not sure I'm following it.
Okay. Does the permafrost risk map assume natural permafrost conditions?
Okay, thank you. I'm not sure how you define natural. I mean, basically, the various measurements have been occurring since the 90s. So there is a bit of a trajectory of change. However, at the higher level scale of modeling we did, the model is basically developed, I guess I would say, for today. So current conditions, but with an eye towards how future conditions would look and how your risks may be higher or lower in different terrain types based on how those future conditions may look. Hopefully that addresses the question.
Great. And I'll make sure you get the transcript of the questions. And as a reminder, contact information for both of our speakers is included in the PDF of the slides that you can download at the link that was shared to you in the chat. At this point, we're going to go ahead and transition to our second speaker, who is Ms. Margaret Kurth. Margaret is a research environmental engineer with SERDP as a practitioner of risk and decision science. Over the past few years, Margaret has been working to advance the concept of resilience into practice across a wide diversity of domains and disciplines with a focus on infrastructure systems. She works closely with domain expert modelers to formulate resilience such that it can enter into analysis and as an objective be traded off with others. Margaret's other research interests include water management, risk communication, and ecosystem restoration. And in terms of academic background, she received a bachelor's degree in natural resource management from Cornell and a master's degree in environmental and water resource engineering from Tufts University. Margaret, we're pleased to have you. Please get started with your presentation.
Thank you so much for that introduction, and thank you for ESTCP having me here. What Tom provided was really great context for what I'm going to be presenting, because it's shifting over from, those really on-the-ground challenges that are faced in the Arctic to slightly more conceptual ones for how to deal with those challenges. So hopefully these two presentations complement each other. I have here somewhat of a rebranding of the title. Initially, we were the Installation Community Resilience Analysis in Cold Regions project. That's still official, but I've rebranded a little bit here as a Mixed Methods Installation Resilience Assessment. And the reason I did that is because resilience assessment to support mission assurance can be a big undertaking. Because resilience isn't one capability, it's a collection of capabilities that take effect at different points in time in a hazard event life cycle. So I want to emphasize here that we're presenting a framework, but the methods that are used to fulfill the framework might need to change from one context to another. I'll be showing here the kind of methodologies that we've decided to use within this framework. Sorry about that. First, a quick overview of what I hope to cover during this presentation. I'll give an overview of how our team thinks about resilience initially, the purpose of the assessment, and then on to those few new methodologies we developed. These include assessment of novel Arctic hazards, a method to calculate a resilience criticality score, and a proof of concept resilience return on investment methodology. And then, of course, I'll get to, just the conclusions and benefits. I'll give you initially a couple of takeaways right from the get-go. We feel that given finite resources, we need a way to prioritize resilience enhancements, and that this can be done based on mission dependency, as well as identified deficiencies in expected performance of different functions and missions. The department already has some very useful ways to categorize assets and functions, and so we've tried to rely on those as much as possible so that these methods can be transitioned not just to the installations where we focused in the Arctic, but also broadly across the department. And we wanted to find a way for end users' needs to be taken into consideration. We essentially define an outcome as being resilient based on whether it meets the end user's needs. So the kind of social component of this was really important to developing our resilience quantification methodology. So hopefully I am not preaching too much to the choir here on what resilience means, but I think that to give you the context of where and why we decided to go where we did, I think I should start with this really quick primer on the way that we decided to treat resilience. Here we have, and actually I was asked not to give a lot of squiggly graphics, but unfortunately I couldn't help doing that. But you'll see here two different y-axes. There's the critical functionality of the system over on the left, and the quality or operation of the infrastructure over on the right. And the thing I want to illustrate here is that we don't want these to completely correspond to each other. We want them to be divorced from each other to some extent, so that if our infrastructure is disrupted, as you can see with the blue dotted line, hopefully we can keep our functions, or in the case of Department of War, we can keep our missions continuous. And so that's really what we're trying to get at here. And what are the enabling factors for divorcing those two things from each other? So to put it very simply, I guess, we looked at resilience as the quality of the system to perform following a hazard. The shape of that resilience function that I just showed you in the last slide is a product of many components and capabilities. They're all essentially building upon each other to create functions and then also to perform the mission. So focusing on system function instead of on specific assets, I believe, and our project hopes, opens up opportunities for creative continuity and recovery planning. Another squiggly graph. This is our assessment framework. And I will try to use my cursor here to point to a couple of things. One key component of this framework is that we want to understand how different hazard scenarios not only lead to infrastructure outage and damage, but we also want to be able to translate those effects into the functionality of the system. So we include that in our system response, as well as recovery, which can be boiled down to things like time to recover and cost to recover. So this in its entirety is system response. We do have limitations in our hazard models in basically extending from damage to functionality. So that has been a sort of critical research question of many resilience sort of researchers over the years. And so that's why I point to things here in yellow, like you may need to take a multi-method approach, and you should ideally be able to rely on past experiences, but we don't necessarily have good databases for things like recovery time and cost. So this is still an evolving framework. But from this, we also want to be able to compare the system response to the user needs, like I described. So we want to develop a sort of level of acceptability, where a system may actually respond poorly, but if that's acceptable, then it's not really a high priority. It's really where there's a mismatch between the system response and the level of acceptability that we should be putting as a high priority. So that then can lead to definition of where is our system deficient, and therefore we should make investments in them. And now I'm going to move on to talking about the different sorts of methodologies that we decided to use to satisfy our framework. And this first one was performed by my colleague, Dr. Matt Joyner, and he is really the seismic hazard expert here, but I'll do my best to explain his work. We focused on seismic hazard, and then another hazard that I've opted not to show here today is icing events, which can lead to very thick buildup of ice on infrastructure that can impede operations. But for now, I'm going to focus just on the seismic hazard for the sake of illustration. We wanted to test whether existing design standards of buildings can be met if their permafrost foundations degrade. And so there are various kind of building codes and standards that are set by ASCE 7. And so we anticipate that ground motion would be amplified if the foundation changes. So we're able to use finite element modeling to simulate all of this with different foundation conditions. And what we found, or my colleague found, was that traditional building designs in his simulations do not meet the standards for ASCE collapse prevention. Let me go on to the next slide really quickly. Here, this graph illustrates the ASCE target, and we perform these simulations under different future scenarios and find that here, for example, the 50-year collapse probability standard is not met. But when we try out different designs, new augmented designs or above code designs, we actually can find that we may only require a very small amount of investment over the traditional design in order to meet the standard. Now I'm going to make a big leap forward from that highly technical piece of work onto a different piece of our methodology. So we really wanted to ask installations and communities about their ability to cope with different disruptive events. And as I mentioned before, we specifically wanted to be able to translate damage of infrastructure into disruption of functions and ultimately into potential impacts to missions. So to draw these necessary connections, we used existing installation systems for categorizing and assessing assets. And the one that I'm showing here is the mission essential function kind of concept, which goes into mission assurance. These are basically functions which have been defined already by Department of War as being critical to mission assurance. There are some other existing frameworks that we also opted to use, such as the Cyber Infrastructure and Infrastructure Security Agency's National Critical Functions, which are actually somewhat simple and similar and overlapping with the mission essential functions. We also can use things like the Builder Sustainment Management condition assessments for individual assets, as well as some usage of the mission dependency index, which some of you may be aware of. Here on the right-hand side is a really squiggly graphic just to illustrate the way that we took many, many assets and we condensed them down into different mission essential functions. And we have lots of information about these assets, so we understand their condition and the dependency of the mission on them. Okay, so to meet our objective of understanding the ability of installations and communities to cope with disruptive events, we designed and administered a questionnaire. Our questions were intended to capture various needs and expectations of different stakeholders. And so hopefully this graphic resembles the one that I showed earlier, where the mission is one function and the in this case, the mission essential function, although this could also just be infrastructure assets, is a separate function that are not necessarily tied together. So we used points on this graph basically to formulate questions for both installation personnel and some community entities about their tolerance for infrastructure outages. So we had them define things like how much functionality or performance can be lost so as to not impact the mission, and how quickly do those things need to be recovered, this next point in time, how quickly do they need to be recovered so that the mission doesn't begin to degrade? So we specifically formulated our questions so that we can correspond them to points on this graph, and then also attempt to apply math to that and develop a criticality score, as we decided to call it. So we did develop this criticality score, and this essentially means that we expect that a mission essential function will not be able to be recovered in time to prevent the mission from degrading. And it's really based on the ability to recover quickly, and that's considering the availability of both internal and external support. For example, we asked an installation, to what extent can you meet your own needs internally versus to what extent do you need external support, and vice versa with the community. Here are a couple of results that I think are notable. The installations that we talked to reported a high level of self-sufficiency, but they did have some dependency on community support for these different mission essential functions: water and wastewater, bulk fuels, petroleum, and food. There were some of the mission essential functions that they had a fairly low tolerance for loss of function. So if they were to lose the functionality for, say, 1 to 7 days, their mission would begin to degrade, according to them. I will report as well that we did not have a really great response rate. Ideally, we would have been able to get more input on these different questions, and there was also a lack of consensus among some of the respondees. Also, in terms of results, this is one example of how we came to certain conclusions. So here we're visualizing the condition of facilities versus the of missions on different facilities. And the different colors correspond to different mission essential functions, which I didn't have space for a key here. But you can see here is that there are some instances where particular facilities are considered to be fairly important to a mission, but might not have a completely ideal condition. So we can use visualizations like this one and others to identify, where there might be certain needs or deficiencies. Okay, so now moving on to yet one more methodology, which I'm actually really excited about, and hopefully I can convey what we decided to do here. So we wanted to calculate a resilience return on investment, and this is really bringing it full circle. Not only do we know where the deficiencies are in an ideal world with our methodology, but now we can also compare alternative investments and figure out which ones give you the greatest bang for the buck. So we wanted to identify investments that would maximize the functionality of a hospital, in this case, following an earthquake on an installation, and minimize the financial cost of keeping that functional. So we set up an optimization with a few different alternative investments, which you can hopefully see here: generator, photovoltaic, battery, and then also the possibility to just harden the substation that's outside of the fence line. We know the demand load of the hospital, and much of this was determined with a tool called Reopt, which also optimizes the size of these for us. So, sorry, next slide. So getting to some of our preliminary results, this is very proof of concept, but one of the key components that we need to be able to have some measure or some output of the functionality of our system here following a hazardous event. And so we've been working on, even for a little while before this project, specifically for buildings, but it also merits some attention for other sorts of systems because it needs to be done differently. Over here on the left-hand side, you can see that we are able to actually create a metric for functionality of a building through time following a hazardous event. And so, and these are quantitative things that we can put then into our optimization. Here you can see that there's a stepwise function or incremental increases in functionality of this building, the hospital, following safety-related repairs. So initially, you'll have some period of time where, you know, first you need to check that your building can be occupied and there's not a collapse risk, et cetera. And then for this particular field, there's actually a good amount of data on how a building is recovered following an earthquake. So we have time and cost data that we can use in our simulations. Over on the right-hand side, we have loss of functionality of the hospital versus the life cycle cost of energy investments to support this hospital. And what we're really looking for here is points like down here on this lower left-hand corner where we're not losing a lot of functionality relatively after an earthquake, and we also don't have a high investment cost in the energy to support the functionality of the building. So although this is a relatively small proof of concept, we were excited to get all the pieces of this simulation and optimization actually working together and create results that we think can be used in a scaled up system and even transferred over to other systems. So moving on to my conclusions, we were able to identify some community installation dependencies. Those were really areas where the installation said, for example, some of their ability to recover was by virtue of support from outside the fence line and vice versa. I do think that there's more potential to explore some of those dependencies and even to formalize them and come up with mutual agreement arrangements if they don't already exist. Also, a conclusion is that this assessment is a mixed method process. And so while I feel that the framework that we've presented here is very solid and can be used for a lot of different systems, you'll likely need to use different methods to characterize your hazards, understand the impact on your systems, understand the recoverability and the repair cost and the sufficiency of that. So different methods should come into play with different assessments. And also that getting to that level of detail can be time consuming. And so we do need to be careful to get beyond just hazard characterization and impact and as far down the line as we possibly can to actually fulfill resilience assessment. Another conclusion is that there are these existing mission assurance concepts that can be leveraged in resilience assessment. And we've tried to tile these things together so we have different angles to look at assets and functions and the way that they support missions. Also, we've presented some methods here, all of which still need to be matured somewhat, but there is opportunity to improve them and even to potentially synthesize them into maybe singular planning tools. And then on to the benefits. So we treat resilience as a design and planning objective, which I feel is helping to advance some of the more recent requirements coming from the department, and it needs to be put into practice with quantitative metrics to the best of our ability. Otherwise, it just kind of remains in conceptual land and can be challenging to use. Enhancing the resilience of functions is more effective given evolving hazards. And this is, going back to moving the focus away from individual assets, that we can probably find more efficient solutions for the department if we think about overall functions and look for opportunities to maximize function and minimize cost instead of on individual assets. And the last benefit is that understanding vulnerabilities that exist outside the fence line is really just the first step to addressing them. But there are dependencies among the two geographies, and they do need to be considered. Oh, lastly, onto my acknowledgements. There's quite a few of us here, and I didn't mention that we did also have a capstone project integrated into this that was conducted over one academic year under the leadership of Colonel Brandon Thompson at West Point, and his cadets created a causal loop diagram to complement our work, and that was a really great experience. I wasn't able to go into a high level of detail about any one of the methodologies that we developed, but if any of them piqued your interest or you have any other reason to contact me, please feel free to do so, and here's my email address and phone number. And with that, I am all done. Thank you.
Great, thank you so much, Margaret. We have a lot of questions that have come in. The first one is from Coastal Engineering and Adaptation Solutions. What does it mean for the collapse probability to exceed 1?
Sure. So I may not be able to speak to that as well as my colleague who did this modeling, but there are different collapse probabilities that are set in building codes. And so when we're doing these simulations with many, many realizations, it's very, very probabilistic. And so we're looking for things like the mean probability of collapse. Unfortunately, I'm not able to speak to whether what it means to be 1, unfortunately. So I'm sorry about that. Only just that we're basically comparing the mean results and potentially other moments to the building code standards to see whether we can meet the standard.
Thank you, Margaret. This next question is from Oak Ridge National Lab. What's the most critical challenge for DOW facility buildings in terms of resilience and functionality at the moment from the utility perspective, such as hot water usage, indoor thermal comfort, space heating and cooling, dehumidification? Can you please speak to that?
Well, no, actually, I'm not able to speak to that. I'm sorry. I'm like being pushed a little bit outside of my expertise with these questions. For those sort of day-to-day challenges in the Arctic and what that actually means for resilience, I'm not exactly sure. We were thinking more about acute hazards and how that might impact the mission. But with that said, some of these acute hazards could impact the lifeline services to buildings that are mission critical. And so at least being able to have some baseline occupancy and usage of a building, I would imagine would be very important. But what exactly that baseline is, I'm not sure. And to what extent can you continue to use a building if you could only say provide a certain level of thermal comfort? I would imagine that is a challenge, but I can't speak to its overall impact necessarily.
Understood. This next question is from the Pennsylvania Department of Environmental Protection. Do you have an example that you can share on how you applied your concept and what the outcome was? Your framework?
Sure. So, well, the framework was guiding all of this work. And so the different boxes that I showed in the framework were basically fulfilled with different methodologies. So really all of this project is demonstrating the framework, We do have other examples of using this framework, which we were developing through this project as well as other complementary ones. So, for example, you could imagine that this would be used for transportation resilience, for energy resilience, for community resilience, even especially when you think about infrastructure system by infrastructure system. I would say that probably the best way to find some of those examples would be to look up the risk and decision science team of the environmental lab of the ERDC, or also you could use my last name or those of the ones that are listed on that last acknowledgements page.
Thank you. Can you elaborate on some of the resilience concepts you drew on when you formulated a questionnaire to ask about mission tolerance to mission essential function outages?
Yes, sure. So I think I mentioned that considering things from the functional perspective instead of from the assets perspective, hopefully will open up creative solutions for mission continuity. And so we're drawing on concepts like redundancy, passive survivability, and mutual aid as some of these potentially creative solutions. So if an asset is not, critically important to the mission, according to, say, its mission dependency index, then you could look for some of these other solutions that you could survive without it for a while. You could create redundancy, or you could find that coming from mutual aid from, another entity.
Thank you. How could you increase your confidence in the responses you got from installations and communities about recovering functions in time to meet their needs?
Thanks for that question. All of the information that we used to create criticality scores did come from responses of installation personnel and some community entities. And as I mentioned, we did have some points where there wasn't great agreement in those responses, or in some cases there were not responses. So I think that one way to improve would be to drill down into individual mission essential functions and do things like a tabletop exercise involving both an installation and community stakeholders. Or potentially there's opportunity to actually do modeling of some of these individual mission essential functions. We were trying to look at the entirety of all of the functions within this project, and really it's too many to be able to get to a high level of detail with each one, but you could choose individual ones, such as, say, like bulk fuels, and conduct more in-depth studies.
Great, thank you so much, Margaret. This next question is from Graystar Pacific, and probably both you and Tom can speak to it. So let's start with your response and then invite Tom to join the discussion. Can you address protection of defense-related infrastructure in the Arctic marine coastal environment, specifically, and then more broadly in the Arctic?
Can you say the beginning of the question again, please, Rula?
Can you address the protection of defense-related infrastructure in Arctic marine coastal environments, mostly ports and harbors, but more generically in the Arctic?
So protection of the coastal infrastructure, I would advocate using even a framework like the one that I've presented here. And actually, this also speaks to Tom's response earlier about airfields, that, not every airfield will be suitable for every purpose. Some of them will be more suitable and more appropriate. And so having some way of prioritizing them and understanding to what extent they need to be protected, I think would help in decision making. So there may be some coastal infrastructure for which we really need to have hardened solutions versus other ones that maybe could have softer solutions, other ones that could have redundancies. So we should prioritize those components of infrastructure and then think about their criticality. Over.
Thank you, Margaret. Tom, is there anything you'd like to add?
Yeah, so Margaret had a great answer. I think I'll build off it a little bit with some work we've been doing. So we have an ESTCP project, a separate one focused on the coast right now. And there's lots of folks working kind of the Arctic and Alaskan coast. The sort of broad questions are, is it a rocky coast like most of Greenland, where you have less of a challenge, or is it a permafrost coast like most of Alaska? I think then you'd say, is there a protective barrier island or not? In terms of protecting it, yeah, you can build all sorts of structures, but moving concrete or rock, especially on the North Slope of Alaska, where you almost have to get it near Nome, anything you want to build is probably in the hundreds of millions of dollars. What a lot of people are doing is repeat optical imagery. You can basically map coastal retreat over time. Repeat LiDAR, you can do that. Plus, you can look for subsidence on land. Like in interior Alaska, you want to avoid high ice content material because that can thermally and mechanically degrade along the coast. Right now, where there is, let's say, DOW or civil infrastructure, a lot of people kind of just are tracking like, okay, this is retreating about 10 meters a year. And so, in 10 years, we'll be 100 meters further inland type of thing. And I know that sounds maybe too quaint or whatnot, but those are some of the ways people do it. The last thing I'd say is one fall storm can do almost a year's worth of erosion or almost equivalent to just a summer of very slow trickling erosion. So predicting that is an added challenge. And then think about flooding too. So erosion's one thing, but flooding's another. And I think we've learned a lot about flooding from the two recent typhoons that hit Western Alaska. Thank you.
Thank you. And this is a question that's applicable to also both of you. So we'll start with you, Tom, before we wrap up. What are some of the emerging technologies you see that will be able to help with land management decisions and activities in the short term or the next 5 to 10 years?
So I guess I would say from a personal perspective, getting some of these surveying instruments onto UAS platforms is allowing us to more rapidly assess real-time or near real-time field conditions. From there, I think a need is adequate ways to sort of run your data through, I guess, what I'd call geospatial modeling or geospatial statistics, right? And again, like I mentioned before, we can measure things at the ground surface really well, and they oftentimes give us clues to what's in the subsurface, but not always. So interrogating those relationships would be sort of a personal goal of mine. Thank you.
Margaret, would you like to add anything?
Sure. I'll just add that I'm a little bit more on the decision-making side than the data collection side, but I think that there's an important sort of bridge to gap there where, not more and more data is not always necessary. And, how we manage that data to inform decisions is really important. So looking at how much information do we truly need to make a decision is I think, of a lot of interest to me. And I think that it's an area that has been of interest in natural resource management for a long time, but is not necessarily solved in a very user-friendly way. Thanks.
Great. I'd like to thank you both for a very engaging webinar. And as Kevin mentioned, on this next slide, you'll see a link that will allow you to view archived webinars and also register for upcoming webinars. I also would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it at this time if you can please take a moment and complete the very short survey that will pop up on your screen. This concludes today's webcast. Thank you so much for joining us.